Welcome to section 8.1, sequences and series, and I know we jumped back to chapter 8 for just a minute, but this is going to lead back into limits on the next day. So we're only going to talk about sequences and series today. We're not going to talk about limits. We're going to find the sum of series, and we're also going to use something called summation notation. You've probably seen that before, to write sums of these as well as a series as well. So two things here. A sequence is just a list of numbers. So it might have a pattern, it might not, whatever, but it's just a list of numbers. 1, 3, 5, 7, 9, and then the next one 1, 1, 2, 3, 5, 8, 13, 21. That's Fibonacci sequence, if you didn't know that. It's one of our famous sequences. And then the next part is, a series. And a series is the sum of resulting from adding the terms of the sequence together. So if we take a sequence and we add up the numbers, that's then called a series. Now, series and sequences can be finite, which means they do end. For example, 1, 3, 5, 7, 9, n. That's a finite sequence. Or we can have infinite. And infinite means they go on. So you can see the dots at the end of here that indicate that the sequence goes on forever. So we'll be looking at both these, sequences and series, today. So the first part we're going to talk about is summation notation. So we use summation notation to show a series. Well, once again, going back to series, a series is you're adding up the terms of the sequence. So here's what we're going to use. This is called, this is sigma. That's the symbol that we're going to be using, but it represents the sum. So with the symbol sigma, we have n represents the variable that we're talking about. So it is, f of n, whatever that input value is. A is the starting value for n. So you have n going to, where do you start the summation? B is where you end the summation. So you have the starting and then the ending. So A is where you start, B is where you end. And then f of n represents the function for finding the nth term of that sequence. And so that's what we'll be plugging in to figure out what the series is. The way this is read is the sum of f of n from n equals a to b, and that's kind of how we read it when we're talking about a finite series. If it goes to infinity, we'll read it kind of the same way, the sum of f of n from n equals a, but to infinity for an infinite series. So this can go on, as we said earlier, forever, and we'll be able to add those numbers up, and that actually gets us back into limits on the next one. For those when it does go to infinity there. So let's look at a couple of these here. The first part here, you're just finding the sum. So this is where you're really just plugging this information in, writing out those numbers like in the series from the first slide. So you'll be saying, 3 plus 6 plus 9 plus 12 plus 15 equals 45. So we'll be adding those up here. So let's just take a look at a couple of these here. So we're going to start looking at a couple of things here. This is just the function n. N's going to start at 0 and end at 7. Okay, so the first one, if we plug 0 in for n, that's 0. If you plug 1 in for n, that's 1. And then you just keep doing this. Plug 2 in for n, that's 2. 3 in for n, that's 3. And you go all the way up until you get to the stopping point where n is 7. And so now you add all these numbers up, and if you add all these numbers up, you will get 28. I believe, let me double check. 10, 22, and 6 is 28. Alright, and that's what you need to do. Let's take a look at another one here, make it a little bit harder than that one. This one is 2k minus 5, so you can see you don't have to start with n. We're using the variable k on this one. That's fine as long as your input value matches up with where you're starting and ending, so don't use different variables there. I'm going to write this all the way out on this. So we're going to start with k equals 3. So this would be 2 times 3 minus 5. And that will be the first number that we will add. Then we'll say plus, and then we'll go to k equals 4. So it'll be 2 times 4 plus 5, or minus 5, sorry. And then when k is 5, it'll be plus 2 times 5 minus 5. And then we'll do k is 6, and we'll keep going. 2 times 6 minus 5 until we get up to k equals 8. 2 times 7 minus 5. I'm going to run out of room, so I'm going to put it right below. 2 times 8 minus 5. And so we got all the way up to k equals 5, and then we'll stop. So what are these numbers going to be? Well, let's calculate. 2 times 3 is 6. 6 minus 5 is 1. 2 times 4 is 8. 8 minus 5 is 3. 2 times 5 is 10. 10 minus 5 is 5. And you'll start to see a pattern here. 12 minus 5, 14 minus 5, and 16 minus 5. So when you're going up by repeated addition, that represents, when you write the sequence here, the function, it represents multiplication. Repeated addition is multiplication. And so what does that add up to? 1, 3, 5, 7, 9, and 11. That will add up to 36. So the summation of that function 2k minus 5 from k equals 3 up to 8 will equal 36. On the next one, go ahead and try those two on your own. Set those up and plug in 0 for this. And so you'll have, and you might want to pause it and just try to do these on your own. You'll do 4 raised to the 0 power plus, oh, I'm doing a video, I'm sorry. Okay. Then you'll have 4 raised to the first power plus 4 raised to the second power plus 4 raised to the third power. And so what you'll do is you'll just add those once again up. Make sure you start at j equals 0 and end at j equals 3. So 4 to the 0 is 1. So it'll be 1 plus 4 plus 16 plus 64. And then that will add up to 85. And then you have your last one. Now the last one, pay attention to the last one, because the last one actually goes to infinity. So we're not going to obviously go up to infinity. We'll have to stop at a certain point and see if we can figure out where it is going. So it's 1/2 raised to the n. So 1/2 raised to the 0 plus 1/2 raised to the first, 1/2 raised to the second, 1/2 raised to the third. And let's see if we can figure out what's happening at that point. So anything raised to 0 power is 1. Then you got 1/2 to the 1 is 1. 1/2 to the 2 is 1/4. 1/2 to the 3 is 1/8. And once again, kind of keep going there. So if you add those up, what's happening? Well, you adding, you got the 1 here to begin with. But then at that point, you're adding the fractions 1/2, 1/4, 1/8, which is half every single time. So if you want, you can try to plug that in your calculator and see, what's going to happen there as it gets closer and closer. So I could go over to the calculator and do 1 plus 1 divided by 2 plus 1 divided by 4 plus 1 divided by 8 plus 1 divided by 16. And you can keep doing this for a little while and look what it is doing. And so if you want to try again and then add another one, what does it look like it's getting closer and closer to? 1.98 now. Alright, so maybe we can assume that we think this is going to the value of 2, which would be correct. And as you can see, if you start thinking about that, that kind of represents a limit. As you're getting, adding these numbers up, what is it getting closer and closer and closer to? So maybe that'll give you an idea as to where this is actually going to go the next day. And so that is equal to 2. Alright, so now that's kind of the first part, is just being able to plug in the information, figure out what that series looks like, add up the numbers, and then find the value. Now I will tell you, on your calculator, I don't know if it's on this one or not, but there is a summation symbol. On mine, if you go to math and you go far enough down, you might find it on yours. It's right here. I'll have to show you in class how this works because it's a little different on this calculator, but I can show you how you can check your answers to see whether you got the right values on these or not. So I'll do that in class. The second part of this is actually going backwards, which is usually the little bit more challenging. Anytime we work backwards, it's a little bit more challenging. So I'm going to give you the summation. I'm going to give you the numbers that we're going to add up. And I don't want you just to add them up and tell me what the answer is. I want you to create the summation based on that information. So you're really looking for patterns. All right. So the first thing is, on the first one, what do you recognize? Well, you're going from 3 to 6. You're adding 3. 6 to 9, you're adding 3. 9 to 12, you're adding 3. And 12 to 15, you're adding 3. So repeated addition is multiplication. Repeated addition is multiplication. So when I go to set this up, the summation here, all right, of the function, well, repeated addition is multiplication. So if I just take 3 times n, is that going to work? Well, where should n start? What do we want n to equal? Well, if I want 3, then I want n to equal 1. 3 times 1 would be 3. And if I do 2, 3 times 2 would be 6. 3 times 3 would be 9. 3 times 4 would be 12, and 3 times 5 would be 15. So it looks like we have the answer. We want to start n at 1, and so n would be 1, 2, 3, 4, and 5. So we'll go all the way up to n equals 5. And there you go. You just work backwards from the summation, looking for that repeated addition. I'm going to skip down to E, because I want you to see this. So if you look at E, and you look at exactly what we just did, we got plus 3, and plus 3. Repeated addition again. So how is that going to work on this one? Well, you still have the repeated addition, 3 times n. But if I start at n equals 0 or n equals 1 or wherever you want to start, if I just plug that in, that's 3 times 1 is 3. But we're starting at the value of 10. So what do you have to add to that to get 10? Well, you'd have to add 7. So will that work for the next term as well? 3 times 2 plus 7. That would be 6 plus 7 is 13. And since you're doing the repeated addition again, the 7 just gets you to kind of that starting point. And then this would give you 16, and so on. So that is the pattern, and you would go up as n is 1, 2, 3, and 4. You can go all the way up to 4. So just because when you see that repeated addition, you've got to be thinking about that's your multiplication. Whether you start at 3 or whether you start at 10, as long as you're going up by 3, you might have to add something to that to create that starting value. This isn't the only one. You could actually, what happens, how would this change if you started n at 0? Well, now it's 3 times 0. Alright, so 3 times 0 is 0. So then it means you'd have to add 10. Well, would that work on the next one? Well, if n is 1, 3 times 1 is 3, 3 plus 10 is 13, which gets you there. But now instead of going up to 4, it'd be 0, 1, 2, 3. So that would be 4 terms still, but it's going to keep going. But the other thing is, we got some dots at the end here. So it's not even that, it actually goes up to infinity because it keeps going. Alright, so that's kind of a way to look at it. So maybe stop the video and try B, C, and D on your own. There is one more repeated addition. So you can look at D, that's another repeated addition problem. And then B is actually a multiplication, so we'll talk about that one. And then C is kind of a special one. It's not addition or multiplication. So maybe try D on your own, and then we'll look at B. Alright, so on D, you're going from 24 to 19, that's subtracting 5. 19 to 14, subtracting 5. And so there's your repeated addition. Yes, it is adding negative 5. So you know it's going to be negative 5 times n, k, whatever letter you want to start with, or your variable, negative 5n. And then where do you want to start n? Well, if you start n at 0, then what are you going to have to add to that? Well, it starts at 24, so you want to have plus 24. Will that work for everyone? Once again, yes. When you plug in 1, it's going to be negative 5 plus 24, 19. Plug in 2, negative 10 plus 24, 14. And you're going to go all the way. So if you start at 0, this would be 0, 1, 2, 3, 4, 5. So you're going to go all the way up to 5. That's a total of 6 terms when you start at 0. That's not the only way that you could do that. You could do that another way, starting at n equals 1. So you have some options on these. All right, let's go back up to B now. All right, on B, we're looking at how do you get from 3 to 9? Well, yes, you add 6, but you don't add 6 repeatedly. On this one, you multiply by 3. Multiply by 3. So this is what we call a geometric sequence when you're multiplying by 3, or a common ratio. And so what do we do here? Well, repeated addition is multiplication. Repeated multiplication is exponents. All right. So the common ratio is 3. But you will be raising it. I'll make this one just a different variable, not that it matters, but so we'll be raising it to the power of k. Well, if we want it to be 3, if we raise k, 3 to the 0 power, that would be 1. So we want to raise it to the first power. So 3 to the first is 3, 3 to the second is 9, 3 to the third is 27, and so on. And then how far do we want to go? Well, we got k to the first, second, third, fourth, and fifth, so we'll go all the way up to 5 for k. And there's an example of repeated multiplication, which is dealing with exponents. And so that's a geometric sequence. A, D, and E, those were arithmetic sequences. And then the last one here on C. So if you look at C, you got 1 over 1, 1 over 4, 1 over 9, 1 over 16, and then it jumps and then goes all the way up to 1 over 10, or 1 over 100. Well, what's happening? Well, the 1 on top is just staying. So that means there's a 1 on top. What's happening to your 1, 4, 9, 16? Those should look very familiar. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and then you get up to 10 squared. So what's happening? Well, the bottom term is being squared. So whatever you pick for your variable n, you want to square it. So your denominator is going to be whatever term you're looking at squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, and so on. And so you're going to go all the way up to 10 squared, so this one goes up to 10. And there you go. And so that takes care of that one as well. So you're going to see the geometric and the arithmetic sequences. There are formulas for those that I am going to show you on this next slide, but you also can just kind of work your way through it as well, knowing that what repeated addition is multiplication, repeated multiplication is exponents and things like that. But look for those patterns is what you're looking at. All right, here is the last slide if you want to write this down. Geometric sequence, the formula for that is that A times R raised to the K. A represents the first term. The information is down here. And then the R is the common ratio. So what is being multiplied when you do that? Now on this formula, it's actually starting at K equals 0. So you would use this when K would be equal to 0. And then your arithmetic sequence, same thing. Now its arithmetic sequence has a common difference. So you still have your first term plus K times that common difference. So that's what I was talking about. What's being multiplied? So when you go back and look at that common difference, as you go through here, you're adding 3 every time. You're adding 3 every time. You're subtracting 5. That's your common difference. That's what I'm talking about when we talk about that common difference. All right. And there you go. Once again, you're starting at K equals 0, and you'll go up to n minus 1. N represents how many terms that you have or that you're talking about in your series. So if you struggle with working backwards, then this might help you identify some of those things to make it a little bit easier on you. All right, that is it for sequence and series. Thank you.